the recordings of all, there've been a total of 5 live lessons, and they're all posted. And I also posted the notes from these sort of whiteboard things. Hold on, let me I have to change a quick setting here. I was able to find all except for one of those. So so you have more resources for you. Okay, now Scott, you had a question that you were asking just before?
No, it was me. Grant.
Oh, Grant.
Yeah. So I had a question about the geometric thing. It might be easier if I share a screen. Is that okay?
Yes.
Okay. So I'm curious. You all can see that now. Why, if you get the perfect square that's the closest to the square root you're looking for, and you're only looking for that last digit, basically.
Yes.
I'm curious why you go through the step of guessing when that last digit has to produce a perfect square between 1 and 10. And so you can relatively quickly see that all the ones that end in 4 have to be a 2 or an 8. The ones that end in 6 have to be a 4 or 4 or 6. You know what I mean? Like, you don't have to go through the process of guessing all these different digits. Like, you can relatively quickly pop out which one.
Well,
Like,
if it's the last digit, yeah. If you know it's a perfect square, then you can do the last digit that way. But if you don't know it's a perfect square, you can't. And also, of course, you have the middle digit if it's a 3-digit answer, and that there's no sort of way around it, right? Oh, are you saying, I'm looking here, you're number 3, and I see you have 230. Does that mean you started with 230 as your first guess? Like it was between 230 and 240?
Correct. And I don't need the quadratic part of the thing because I can use the picture to fill in everything. Like,
yes. So I have 2 things to say about this. One is that if you know it's a perfect square and you get to the very last digit, that would really, you would be able to jump straight to it. But it might not be a perfect square. I mean, yes, on the final, I'm going to make it a perfect square, but I'm more concerned. I'm not concerned about that. But there's a problem with question number 3 that I want to go over. So let me first write down what you have for 5, 5, 2, 2, 5. I'm just going to draw here. I'm going to go back to my screen now.
Okay.
But yes, you're right. If you know it's a perfect square and you get to the very last digit, you can do that. However, what I didn't, what I'd rather see when you have this question, it looks to me like you said it's between 230 and 240.
Yes,
and you went like this. This looks like what you did, if I'm correct. And then, however, that's not for the 3-digit one. I want you to do it in 3 steps. So in other words, your first step would not be to get it so fine. You would just be able to say it's between 200 and 300. So your first step would not be chopping off a 230 by 230 square. Instead, your first step would be to chop off a 200. So your first step is just some multiple of 100. Because imagine this thing had like 10 digits in it. There's no way you'd be able to getting all except the last digit will be practically as hard as getting the answer itself. So yes, this has 3 digits, and with a calculator, we could mess around and say, oh, I tried 230. 230 was too small, 240 was too big, so it's between 230 and 240. But I don't want you to get that refined of an answer on your first step. I want you to start with what multiple of 100, what 2 multiples of 100 is it between? So it's between 200 and 300. That would be 40,000. And that if, see, I don't recommend using the square dissection method for these, 6-digit questions. I prefer that you do this one, 55225. Let's go like this. I'd rather you go like this, although this will show you how you could, if you like that square thing, you could, it's kind of like this. We don't,
Yeah.
we don't write this thing usually, all this S, but let's just say, see 15225, if I come back to here, if you wanted to, because I never showed you really, this is 15225. Now, we would say, it's a little tricky here. This thing, my next step wouldn't be to get straight to the, whatever the answer was, 35 or whatever it was, but to get this next sort of piece of it. Sorry, I would be trying to get this whole piece, but I would say 200x here, here's x, 400x, that's 200x down here and 200x there, plus x squared would be equal to 15225, which should be x times 400 plus x. But in this case, you would not be trying 1, 2, 3, 4, 5, 0, 1 through 9 for x, because it's between 0 and 100 now, because we know that the first answer was between 200 and 300. So x is between 0 and 100, not between 0 and 10 now. And we're not going to try 0, 1, 2, 3, 4 up to 100. So instead, we just try multiples of 10 at this point.
Why
And
multiple?
what did it end up?
And it has to be a multiple of 5 because it ends in a 5.
Yeah, but we're not going to be thinking that far ahead at this point. Because what if this was a 6 here and it just wasn't a perfect square? So we're going to do this so that we can do it even when it's not a perfect square. So multiples of 10 aren't going to end in a 5. So if you try now different multiples of 10, what ended up becoming the answer to this question? Was it 235?
Yes.
Oh, let me go over here. 40 blank times blank is less than or equal to 152. So it ended up being 43 times 3 is 129. But come back over here. And really what we're doing is saying x equals 30. So we're doing 430 times 30, which is 12900. And we would subtract that away from the 15225. And we have what's left over would be these little tiny pieces. Now those little tiny pieces would be 230, because this is 30 now. So this square here would be a 230 by 230 square. In fact, this is how you did it at your first step. So I can actually put it in like that. And this is 230x. So it's 460x plus x squared equals, whatever it was, 2235. And then you got x equals 5 that way. So you skipped a step when you jumped to 230 as your first estimate. If it's a 3-digit answer, your first estimate is just going to be a multiple of 100. It's not going to be so refined. Now, that's why I recommend instead not to use the geometric picture, but instead to use the long division algorithm.
Yeah, I tend to like the geometric because it's far more intuitive, and like from a teacher perspective, students really hate long division in a way they don't
Mhm.
geometric
You
pictures.
make a really good point. And I have no problem. This is 465 times 5. I have no problem if you want to do it this way, but don't jump straight to the 230 on the first step then. So you are permitted to do it, but you'd have to do 200 as your first thing.
Gotcha.
Now, if you have a calculator and you know that it's going to be 230, it makes it pretty easy to do this because you make the 200 and then the 30 is going to be there. But
I will
very
say,
good.
though, like you're always going to know that your last digit is a perfect square of 10 if it's a perfect square. And you can see that really easily right away what it is or what two things.
Well, yeah,
Yeah.
if it's only because you know that I'm promising you that the answer is going to be a perfect square.
Right.
still
And I
wanna
knew
see
all
you,
the
like-
homework was too. So that's why I went.
Yes.
Yeah.
No, I understand that. Now, yesterday we finished up with seeing that in China, like in all the cultures, they came up with the Pythagorean theorem. Which they called the Gogu theorem. The Gogu being their words for the two legs of the right triangle. Now, chapter 9 is a collection of 24 word problems. And you can, in the Google Classroom, I just put this up recently, but if you go to where it says, oh, and over here, you can see I put down whiteboard notes. So there's a folder here. So I'm going to post these whiteboard notes each day also. The more resources you have, the better. So class number 8, I have a 2 links. One is for a Desmos, where you're going to put your answers. And one says Gogu problems all. Without answers. So here are the translations of the 24 problems. Now, they did not have diagrams, but some of them are really hard to understand what they're talking about. So I added for question 4 and 5 and 9. Those were the hardest ones to make a diagram for, so I added those. You can see here because the questions have different units, I just want you to know that they have this unit, a chi, which is kind of like a foot, like a meter, like that kind of size. And a kun is kind of like smaller, it's like an inch. And a zang is bigger. I'm not exactly sure what the conversion of these. I guess we would know by saying like a log, some of the things. A tree is 2 zang high. So a zang, is big, it's like at least 10 feet. So just for measurement, a zang is a large unit, like 10 or 15 feet big. A chi is like 1.5 feet, 2 feet, and a kun is a smaller unit, like something in the neighborhood of an inch for measuring small things. Now, the first 3 questions.
Yeah, Professor, are those in base 10 though?
Yes.
Okay.
Yes. Now, I never mentioned the Chinese number system. It looks a bit like the Egyptian system, with like almost like Roman numerals with like a symbol for 1 and a symbol for 10.
Uh-huh.
But in China, they had the abacus, and the abacus, which I'm not expert on it, but I should mention it since we're talking about China. So the abacus has these like wires. Oh, sorry. The abacus has these wires, and on them you have like 1, 2, 3, 4 beads, and 2 up here, and 4 beads, and 2 up here. And the way you would count on it, you'd move the beads. So if you move like, 3 of them sort of up here, that would be the number 3. But when you got to 5, you would move one of the 5 beads up. And then again, 6, 7, 8, 9, and then 2 beads up would be 10. So it's kind of like it has like a base 10, and this is the tens and the hundreds. So it has like a base 10 thing going on, although within the base 10, they have like a base 5 happening. And it's interesting to know about the abacus that they use in abacus, because some of their algorithms were tailored towards the understanding that they were going to use an abacus. So their algorithms are like maybe a little different than we would do with our base 10 number system, but it was because it made sense for them to do with the abacus. And that includes if you're doing multiple calculations on an abacus and you want to like, you're not going to write down your like partial results. You want to have an algorithm so that you could leave the abacus in place. I'm not an expert on the abacus, but I do know that where some of their algorithms might seem unusual, like what they're doing, and part of it is because they're tailoring it towards the abacus and it explains it. But I'm not an expert to say like, oh, I know they did this because if I did it on the abacus, I would do it this way. Now, the first 3 of the problems in chapter 9 are just giving you 2 sides of a 3, 4, 5 right triangle and asking to find the third one. So it says, given 3 chi gu, the go is 3 chi, the gu is 4 chi. How long is this jan? So that one's just 5, 3, 4, 5 right triangle. Here the jan is 5. That's the hypotenuse, and the go. So yesterday I said I wasn't sure which one is which. Evidently the go is the short leg, and the gu is the bigger leg. And the first 3 questions were just, given 3, 4, what's the other side? 5. Given 5 and 3, what's the other side? 4. Given 4, 5, what's the other side? 3. But then we get the word problems. Question 4 all the way through 24 are word problems. And we're going to look at these today and probably spend most of the class period on them. So some of you are teachers already, and other of you are math students, math majors who took math a lot. So when you learned in geometry, they teach you the Pythagorean theorem. Maybe you're in 9th grade or 10th grade. And they said, hey, Pythagorean theorem is really practical. And it is. They're actually right about that. But what are some of the word problems that you can remember doing? Story problems that were supposedly real life applications. You want to type it into the chat? What was going on? What's an example? If you had to make up a word problem to say, hey, it's not just this abstract thing about find the missing side of a triangle, though certainly you did that also. But how would they make that more relevant to your lives? Yes, a ladder leaning up against the building. We have a 13-foot ladder, and we put it 5 feet away from the base of the building. And the question is, how high up the wall does it go? or the length of the ladder. Okay, now I see also something about a kite. That's right. Because, in the ladder question, it's usually the hypotenuse that's known, the size of the ladder. Or the 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 kite question. Actually, the kite question, we probably want to know how high up is the kite. If I know the length of the string, is 13 feet. But of course, any of these questions could be, you could put the question mark anywhere. So kite and ladder. Oh, and I see a few more. Length of a shadow. Here's a tree. Actually, length of a shadow seems more like a because if here's my shadow, it's not like you would know this hypotenuse. Like the length of a shadow is usually, it's a right triangle question, but usually that's like a similar triangles question.
Or a trig question where they're looking for the angle.
The angle here, or you want to know how tall the tree is based on the length of the shadow. But this shadow question, I'm not quite sure. Someone who said shadow question, was the hypotenuse? Because in any Pythagorean theorem question, the hypotenuse is either known or it's unknown.
I was thinking of the height of the tree when I put the length of the shadow. The height of the tree. I recall what's the height of the tree. But it usually was, it involved angles. It wasn't just straight Pythagorean theorem.
Yes. So there's something, or with similar triangles, there's a person and they have a shadow and it's at the same time of day. So the two big ones though are, in my mind, the kite and the ladder. And those are not like the most inspiring questions. Well, I was excited when I dove in to the 9 chapters of the mathematical arts and examined these questions, because there's different ones. We can add, if you're a math teacher, you can add to your collection of the kite and the ladder. Now, I'm going to put you in groups soon, but there are 3 questions, or there's 2 that are particularly that I like a lot. So I want to do those more sort of together. And the first one is question 13. And by the way, in the Desmos activity, which I am going to post the code for, that just has 14 blank pages that let you put your answers into them. It doesn't. I didn't even put the question into it. I just put a spot for the answers. But here comes a code for you. Okay, that's a code that I want you to open, and throughout the class today, you'll be filling in your answers for questions 4 through 14. Now, question 13 says, given a bamboo 1 zang high, which is broken so that its tip touches the ground, 3 chi away from, I need to make this larger. Three chi away from the base, what's the height of the break? Well, that's an unusual question. Here is a diagram. I changed the 1 zang to 10 chi just because, of course, we want to have everything in the same unit. Look at this picture. Look at this wording. And try to interpret how here's the triangle. It's a picture of the bamboo. The bamboo is broken, meaning it's like that. So the bamboo, I'll make the bamboo What is bamboo green before it? I feel like bamboo's green. It's brown eventually. Maybe it's brown. Okay, so there's the broken bamboo. And they say its tip touches the ground 3 chi away from the base. So that's one side. What are you going to call the other 2 sides? Everyone think about that for it and see if you can work out the answer. You get, there's a little surprise in this question. So everyone take about 5 minutes to ponder this question just on your own. How are you going to find the height of the break? And by that, they mean, that's what they mean by the height of the break. Okay, everyone take a few minutes to ponder this question. Oh, and you can put this answer into the Desmos. You know, there's a spot for question 13. It's all the way at the end, but you can go ahead and put your answer into the Desmos. And I'm going to come over here and just watch the answers. There's also a thing you could write on. You know, you could draw. There's like a, they call it a sketch. So you could draw some stuff also.
Professor, should I ask my question about this problem now or should I wait?
Oh, yeah, let's just wait a few minutes.
Okay.
And I'm opening up the dashboard now. So I should see a lot of people on page, it must be page 10.
It's page
So
11.
jump all the way over.
Page 11.
Oh, is it page 11? Page 11. Page 11, yeah. Okay, so good. I see 13 people on page 11, good. Yeah, you could draw a little sketch on it. It's hard with a mouse. If you have it on like an iPad, you could, that would be pretty cool. If you have a computer and an iPad, you could bring up the Desmos on an iPad and then draw more easily. I wonder if people are doing that. Okay, I'm looking over people's answers just to see. I see some pretty nice pictures of bamboo. Ooh, some people typed up their answers. Okay, I'm gonna give you a few more minutes. So I'm gonna mute myself just so that everyone has time to concentrate on this So on that page 11, there's not just there's also on the bottom a box where you could type in. So even if you did it on the diagram, please also type answer into the box. You like whatever your final answer is. Okay, everybody, looks good. Here is the way that I set it up. So the bamboo includes the X and the other piece. So together they add up to 10. So you can call it X and 10 minus X. Hypotenuse is 10 minus X. So then this is really unusual. What is it about this? Unlike the kite and the ladder, what happened in this question? You could type it into the chat. What happened in this question that does not happen in the kite or the ladder problem? So here people saying algebra. I mean, it's algebra. The kite problem has algebra. You know, x squared equals 5 squared plus 12 squared. That's algebra. You know, solving for x. Two people said algebra. So what do you mean by algebra? Because the ladder has algebra. You know, x squared equals 5 squared plus 12 squared, or 5 squared plus x squared equals 13 squared.
It's hard to type in the chat. Can I just say my idea?
Yeah.
So
Yeah.
you only have two known quantities and you need to work with a third, and you kind of have to create a common variable. So you work with a differential to work around.
Oh, I see what you're saying. There's two unknowns, and usually there's just one unknown.
Right.
Mhm.
But you have to create a
Yes.
common variable so that you can solve it. So using the 10 minus X and the X keeps just an X in the equation as opposed to assigning an X and a Y.
I see. Well, usually you just have one letter, you know, because
Right.
but here we have a letter in both things. But what I had in mind is that the x squares cancel out.
Right.
That never happened. You know, like this ends up being a linear equation. It did not require taking a square root at all. So it's unusual. Even if you don't know about how to take square roots, this bamboo question becomes a linear equation instead of a quadratic equation. So I've never seen that in like a Common Core Algebra 1 book, or I actually never saw it in my life before until I saw it in this 9 chapters of the mathematical arts. Now, I should let you know that when they do this problem, they explain they don't like said, they get this answer. And when they explain what they did, they don't have like symbolic algebra like this. That doesn't come till like thousands of years later. Like talking like the 1600s, 1700s is when 1600s is when you start getting like equations that look like this. Even in the 1500s, you had to explain it with all these words, even a simple equation. It was very hard. But what they describe when they say something like of course it's 91 over 20. When they say take 10 squared minus 3 squared over 2 times 10. So that's pretty much what they say to do. Take the length of the bamboo and square it, subtract the break, the distance, and then divide it by 2 times. And it's not clear, like, how did they jump to that? Well, someone in the chat actually made a really good, or no, wait, was it in here? Hold on. Orange, is that what you go by? It says orange flower. Made a really good point.
Thank
That
you. It was me.
Okay. So the really good point is that normally in a ladder or kite question, A and B are given and C is unknown, or A and C is given as B and unknown. In this one, A is given and B plus C is given. Oops. Yeah. So that's interesting. That's a different, and they made like they categorized all of their Pythagorean theorem type problems as, some of them were A and B were given and you were having to find C. Some, in this one, you were given A and B plus C and you were having to find, B and C. Some of them, maybe you were given like A and C minus B, and you had to find B and C. And they turn these things into formulas. So like for this one, the one we just did, they would say take B plus C squared minus A squared over 2 times B plus C. That would give you B. And it's kind of fun. We're not going to do it, but it's fun to verify these formulas. But they had a formula. I think they had about 8 different formulas depending on what the given information was. So someone had to figure out the formula. We don't need to figure out the formula because we can do this because we have our modern algebra. We don't need a formula for every case. We can just set it up and just solve it with algebra. So we're lucky. But they had a formula for every single situation that someone had to figure out. It's kind of cool. I did once mess around to verify these formulas. B plus C squared minus A squared. It's actually hard to do it. I think I did this one by changing A squared into C squared minus B squared. Yes. And then I FOILed out the B plus C squared to get B squared plus 2. Nah, I forgot how I did it.
Hey, Professor, what's that denominator? Is it 2 times B plus C?
Yeah. Yeah, it's 2 times B plus C.
So whatever squared in the numerator is then doubled in the denominator.
Yes. Maybe I could do it that way. If I cancel out the B plus C with one of these, yes, then the other one becomes a B plus C here. And then the c squared minus b squared can factor to c minus b, c plus b. Then the b plus c can cancel. And now I have b plus c minus c minus b, which becomes 2b over 2. Worked. That was fun. Little bit of algebra. Basically, I had b plus c squared minus a squared over 2b plus c. And I had that a squared plus b squared equals c squared. So I'm given those two things. And then I can show that this formula, that it actually equals b. I did that. Whoops. See, I canceled out the b plus c. And then the a squared, I replaced with, because of this, c squared minus b squared. And then the sneaky thing, difference of perfect squares, very important. Algebra, I don't know if they had it, but we do. Then these cancel out. And we end up with 2b over 2. Anyway, I once had fun verifying the 8 formulas that they made up just to see. But back in those days, this question is described as take 10, square it, subtract 3 squared, divide by 20, out comes your answer. Okay, I'm going to put you into groups in a second. The question, whoops, don't look at that. Here we go. 8 and 9, let me just make sure I'm saying this right. Certain questions are like more interesting than other ones. So, I like question 8. No, I like question 6. Yes, we have to do question 6 and 7. Yes, we'll do those together. Then I'll have you work in groups on the other ones. Six and 7 are good questions. Let's see which one we should do first. Yeah, 7 kind of reminds me of number 13. It says there's a rope hanging from the top of a tree with 3 chia of it lying on the ground. When it is tightly stretched, so the end just touches the ground. In fact, let's put you into groups for this. So let me do this. Today we're going to go into groups of 2. So I'm going to make a lot of groups. And then I'm going to combine some of the groups of 2 into groups of 4. So we have 21 people. So I'm making 10 groups. I'm making 10 groups, groups of 2 or 3. So if there's already 2 people in a group, go to go to a group with someone with 1 in it. And let's make groups 1 through 6 will be math teachers. And so groups 1 through 6, actually 1 through 7 will be math teachers, and groups 8, 9, and 10 be math majors. Okay, so we are working now on question number 7. I didn't give you a diagram for it. Let's give you 5 or 10 minutes for that. It's a pretty fun question. You can bring up your Desmos and have someone draw on it. So this is on page, because it's question number 7, it's on page 5 of the.
You mean question number 8?
Okay, I'm about to create the groups now.
Oh, we're doing question 7?
question 7. It's on page 5. Okay, rooms are being opened now. 1 through 6 are math teachers. 1 through 7 and 8, 9, 10. In fact, I just realized I could rename the group. Hold on a second. Rename math major 1. I'm renaming rooms 7, 8, 9, and 10 to math major 2. You'll see this in a second. And math major 3. In future days, I'm going to rename the rooms before we start class. Okay, 2, at most 3 to a room. Open all rooms.
Hey, Joel, do you want to partner up?
Sure.
What room are you going to?
Should we go to 4?
Okay, Professor, can you send me to 4?
Yes, sending you to room 4.
Thanks.
Wait a second. Oh, here you are. Okay, into room 4. Oops.
Oh,
Okay, everybody. I'm gonna keep you in those rooms for when we go back in, but take a look. I have up on the screen, it's kind of like a before and after picture. You've got the vine hanging down. So x minus 3 is the part that's vertical, and 3 is the little part that's hanging, that's left over. Then if you stretch it out from that same point, you end up with this kind of like after picture. So the hypotenuse becomes the sort of stretched out vine, and the 8 is given. And using modern math, we can create this equation. X squared equals x plus 3 squared, x minus 3 squared plus 8 squared. Some people did x and x plus 3, and that's allowed. If you called the smaller one x and the bigger one x plus 3, that would work. You just needed to add 3 then if they asked you for the size. So x plus 3 or x minus 3 would work. And you get 73 over 6, which is 12 and 1/6. Now in the actual 12 in the 9 chapters, they would call this a question where b is given and c minus a is given. And their formula was c minus a squared plus b squared over 2 times c minus a. I'm not going to ask you to verify these formulas, but I've gotten the hang of it now. I divide everything through by c minus a and get c minus a plus b squared over 2, but b squared is c squared minus a squared. Oops, that has to be over c minus a also. And that turns into something like that. Well, maybe I'm not as good as I thought. Now we've done 2 questions out of the 11 that I'm most interested in. So there's 9 more questions. I would like you to try to do 6, 8, 5, and 14, those 4. 14 is so difficult that you might give up on 14 and just mess around with the other 5, which aren't like so bad. I think I want to give, oh, what time is it now? So I feel like I want to give you a good hour of work on these, which means I want to do the break now. So let's take a 10-minute break right now, come back at 10:50, and we'll get intensive work where you're going to work on 9 problems with a partner. Okay, everybody. So I'm going to put you into these groups again. And I think I want to give you about 40 minutes. I think that should be good. Because then I could teach one more thing today, so that today's not just on these questions. But I'm going to give you 40 minutes now and put you back into those groups. 6, 8, and 5 are the most feasible questions. 14 is a major challenge. And if you spend 20 minutes on number 14, that would be time well spent. This is a fun, really interesting question. And then the other 5 are more traditional, but 4 is like totally out there. I just want you to mess around with these questions. So 6, 8, 5, most important. 14 is a good one. If you don't like 14 though, you're not getting anywhere with it, try to look at the other ones. Oh, someone is coming in. Okay, so I'm putting you back into the, oh, I see, waiting room. There we go. Okay. Breakout rooms. Okay, so I'm gonna, oh, I wonder if I can put a timer on it. Let's see. Oh, cool, save breakout rooms. I didn't even know I could do that. Okay, I'm opening the rooms. I'm gonna give you 40 minutes. That means till about 11:30.
Is there a
There you go.
reason you have a question?
Professor,
Yes,
before I join a breakout room, I have a question.
yes.
So I submitted the homeworks 1 through 4, but I noticed that there's also supplemental for the math major, so that's additional work to submit.
Are you one of the math majors?
Yeah,
Are you a math major or are you in the education?
I'm a math major.
Yes. So for the math majors, so far there's been 3 extra assignments. These supplemental math major assignments.
Yeah.
So make sure you do those also.
Okay. And for Delta Math, I completed all the late ones.
Okay, I'm
the
going
one
to
that
give
says-
I'm going to give full credit for those.
All right.
I just haven't done it yet because I have to go in and change it.
Got it. And which breakout room do I join? Oh, it says math major.
What was that?
I was gonna ask which breakout room, but it says math major 1, 2, 3.
Yeah, which room do you want me to put you into a room?
No, it's okay.
Okay, everybody, welcome back. Hold on a sec. Okay, so those questions, I hope you had like some kind of fun thinking about them. Once you see them, the answers after the fact, they don't seem that bad. So I think I'll do 6, 8, 5, and 14. And for homework, have you mess around. If you know these 4 plus the 2, if you know these 6 questions, 13, 7, 6, 8, 5, 14, that's enough questions. I'll probably, on the final, I'd probably pick one of these 6 questions, 13, 7, 6, 8, 5, or 14. And I would just change the numbers. So if you know how to do it for the actual example, you just have to change the numbers around to do that for the final exam. Let's see, for number 6, let's see which one that is. Oh yeah, X. So for number 6, we have this. It looks like this. That's the reed. And we know that it's sticking out 1 above the river. Actually, I can, if I want to know how long the reed is, I can call this whole thing X, which would make this little piece 1 and this little piece X minus 1. You could also call the smaller one X and the bigger one X plus 1. Just know they're asking about the reed. Now they say if I take the reed and I kind of drag it to the edge here, now it just sort of touches the top. And they tell us, if I have this right, I think this is going to be a 5 here, because they tell us that the entire thing is 10 across. So from the middle to the edge is just 5. I know that they said a square. I really picture this better in a circular pond with radius 10, because that way, no matter where you bring it, it's going to be moving 10, whereas a square, if you're from the center and you go this way, yes, sorry, that's radius 5, I mean, that would be 5. But if you went somewhere else, it wouldn't be 5. So I'm not thrilled with the way they describe this as a square and with no diagram. Oh, hold on, somebody's texted me, that's okay. I'll just see. So this was the picture after all, and the length of the entire reed is X. I'll put that here. So our triangle is 5 squared plus X minus 1 squared equals X squared, and that eventually becomes X equals 13. It was a 5, 12. It was the 5, 12, 13, 5, 12, 13 triangle. So that one was number 6. Question 8. Question 8 is an interesting question. We have our pole balancing against the wall, and then we move it back 1 foot, and then it's like totally on the ground. So it's like this. This is 10, and we don't know how big the pole is.
So Professor, can
Now-
I just say something about this problem? We really got stuck with the fact that the person's holding the pole. So how can you say use the 10? Because if they're holding it, they're going to be several feet off the ground.
Let me look at the wording of the question again, just so that I have it. Hold on.
Because obviously a wall goes from the top to the ground. Person's holding it because you got to step back, right? Hold it.
Let me take it here. Let's see the wording. Go problems. Was this this is question number 8?
Yeah, because we were coming up with.
Okay, so the wall is 10 high, a wooden pole is rested, so it's 10. So here we have the 10 and the X. There's our pole. So this is before anything has happened. If one steps backward a distance of 1 chi pulling the pole falls to the ground. It's not worded very well, but what they're saying is if you take, let me make it a different color. Now keep in mind, on the final, I would literally take this question and change the numbers. So as long as you know, even if you don't think this question is worded so well, once we will agree upon like how to interpret it. So what they're saying is that, you can take this red right here, you can
Professor, we can't
drag
see what
it.
you're writing.
Yeah.
Oh, thanks. So what the person is doing, and it's hard to visualize, but what the person is doing, here's the person. And they are pulling this red part in this direction, sliding the bottom of the pole. Now, when you pull the pole in this direction, it ends up going like that, right? The pole, this part of the pole slides down the wall. The top slides down until eventually the pole is completely flat.
Okay.
We start this. This is getting too cluttered. Now, so here's the 10. Now this is not going to be drawn very well to scale. So they're saying that when you pull it back just 1 foot more, it's funny because when you pull it back 1 foot, it's not like it slides down 1 foot. It wouldn't. You could test it with like a pencil and like moving it, but pulling it back in this direction 1 foot does not make it go down this much 1 foot. It's at a different amount. So they're saying that when you pull this back 1 foot, the pole will be completely on the ground. Which means that this portion, which I'm going to make green, would be x minus 1, because this whole thing is x. This is the pole after, and this was the pole before. So the pole is x in both times, but because they're telling us that the pole ended up on the ground when we pulled it back just 1 foot. If this is x and this is 1, this is x minus 1, and there's our triangle.
Yeah, but let
X
me ask you
squared.
this, how can you use x for the hypotenuse and the leg, because we don't know that they're equal in value?
Oh no, it's not the leg.
I was
it's-
wondering the same thing with the other problem as well.
It's a portion of the leg. So the x is, I'll use a highlighter now, make it skinnier. Here's an x here, and the other x is from here all the way to there.
Yeah, but if you use two
That
x,
second x is not the leg.
but it's the
The
base.
x isn't the leg.
The
Go
x
ahead.
minus 1 is the base of the triangle.
That's right. It's smaller.
Right, but you're also saying the hypotenuse has the same length, right? Or just 1 unit different. How do we know it's only 1 unit different? The pole could have been 14 feet long and you could have been 5 feet away from it. So why can you?
But they told us that we only pulled the bottom part back 1 foot.
I agree with the one,
But
part, but I'm having a problem understanding how you can use the same variable for different measurements
because he said that when you pull the pole down, it's going to match the base.
Right, the pole falls to the ground.
Oh, I get it now. Gotcha.
Oh, thank you, everyone. Yeah, so this is the pole before,
Gotcha.
and here's the pole after.
I got it. Okay. My bad.
It's pretty confusing because we only pull, so this pole here, we're splitting up into 2 portions, 1 and x minus 1. Together they become x.
Wow.
It is a little bit odd, like physics wise, that you pull back the pole just 1 foot and the pole's now landing totally on the ground. The top of the pole, went down by 10 feet. It's a little weird, like physics wise.
Yeah.
But I'm glad I heard an aha. So that explanation was working better than what I was saying. And then we have our equation, x squared equals 10 squared plus x minus 1 squared. X squared equals 100 plus x squared minus 2x plus 2. 2x.
Plus 1, no plus 2.
2x is 100, oh, as 1, right? 2x is 101. So x is 50 and a half.
Wow, that is quite the problem.
Now, if you double both sides, if you double all sides of these, it becomes 20, 99, 101. Apparently, that was a Pythagorean triple that they were aware of. That's an unusual question, but if you know these 6 questions and one of them comes up on the final, you know, I hope you'll say, well, that's fair. There's 6 like weirdly worded word problems that I'm going to be like ready for. So that was question number
8.
that was question 8.
So it's kind of like the last problem, but just flipped upside down. Like
Well,
imagine
in a s-
8
yeah.
is now in the water.
I guess it is a little bit like that. This 1 is kind of like above. It's like it's basically the difference between the two things. Now this next question is pretty unusual.
This is
They
number
say
5.
the circumference 5, yeah. The circumference is 3. And we have this vine going around 7 times. And then they say we stretch it out. They want to know how long the vine is. They tell us the height of this thing is 20. Now, this is pretty hard to visualize. I actually have, here we go. Check it out. Animated.
Wow.
I think can I make that a little bit larger? Let's see. Okay, so let's look at this a little more.
That's so cool.
So, oh, and here's a picture of the that other one. Actually, I think I could demonstrate this better if I just let me stop sharing my screen, and I can show you old school with a piece of paper. Hold on, let me get a fresher piece of paper. So if you take a piece of paper and I'm just going to make it into a right triangle. Here's a right triangle. If you roll this right triangle, that didn't work out well. Let me see, how can I say this? I have the right triangle. If I roll it around my finger, oh, this is terrible. I see, because I have to roll it this way. Okay, let me just get it rolled and then I'll show you. Okay, I rolled it up into like a tube. But look what happens when I unroll it.
Oh, wow.
It turns into a right triangle. So coming back So some of you, usually when people are working on this problem, they start trying to figure out, okay, the circumference of the tube is 3, so the diameter is this. None of that actually matters. Because when you unroll it, this thing ends up becoming 21, which is 3 times 7. Because if sometimes I imagine, what if it wasn't winding up? What if it was all on the bottom here? And you went 7 around? When you unrolled it, this would be 21, 3 times 7. And then you end up with a right triangle. X squared equals 20 squared. Sorry. Yeah. X squared equals 20 squared plus 21 squared. X ends up being 29. Nice number. That's the 20, 21, 29 right triangle. Now, this is very hard to visualize. I'm going to recommend that you make a paper right triangle and roll it starting at the thick side. And you'll see, maybe I'll do this a little slower. See when I roll it, you see how the hypotenuse is turning into like a spiral thing. I know. That's actually one of the math majors, students, not the kid. Sorry about this question being kind of hard. No, I know people have families at home. Sometimes I have to pause because I have a 14-year-old screaming at me. Oh, Marcus?
Can we do that for the final? Can we roll paper up like that? I'm just saying,
Yes.
really? Okay.
You'll have your test. You could roll up your
teacher
if
made
your
us do
test is
that.
rolled up like this. I'll just unroll it and integrate it that way.
All right, cool.
So for your purposes, actually what you can do is then kind of after you roll it, you can kind of like trace the hypotenuse, and you'll see that it will make a nice spiral.
Hey, Professor, I have a
But
question.
for your purposes on this question, if you know, okay, it's a right, even if you have trouble visualizing it, just know that the hypotenuse is the vine. The 20 is one side, that's the height of the tree. And the base will just be the circumference of the tree, or the pole, whatever it was called, times the number of times that it wrapped around.
Hey, Professor, I have a question. Is there any way this
Yes.
question could ever result in the wrapped vine being the hypotenuse and not the base, or is it always going to be the base?
Wait, which thing is always going to be the base? The 21,
So when I watched you do your visual for a second, I thought you were going to tell me the 21 was the hypotenuse. So I just want to make sure there's no way when you have a vine wrapping around a tree that ever could result in the hypotenuse and you find the base.
Right. Because if you look at the bottom part, when I make my 7 unrollings,
Yep.
each of those little pieces is going to become 3 on the bottom.
Gotcha.
Like if it was a cylinder, imagine it was a cylinder and not a triangle.
Yep.
And you unrolled it 7 times, it would be 7 times 3. That's the base. The base is always going to become the because the base doesn't really represent, that 21 doesn't represent like a vine. It represents what the bottom of the sort of the circumference, the base of the cylinder. Like if
Right.
the vine, instead of being wrapped and going up as it goes, just wraps around the bottom 7 times.
Right. Okay. Thank you.
Anyway, for our purposes though, on the final, honestly, if you just have memorized, okay, I'll just take number of times around multiplied by circumference, I'll be perfectly fine with that. Okay, now we have 20 minutes left today, and I am actually going to do one more thing. And the reason I'm going to do this is because I want to finish the Chinese math.
Oh, you didn't go to question 14.
Yeah.
Oh,
Are we bypassing
thanks.
it?
No, I forgot about that. Okay, question 14. Now, question 14 is so hard to figure out the slick way to set it up. So you could do this many ways that are very difficult, but there's actually an easy way to set it up. And once it's set up that way, the whole question only takes a few seconds. So let's look at the wording. I actually am really fond of this question because I was so, it took me hours the first time I did this question. Two men stand at the same points. One walks with rate 3, B walks eastward. Let me just get my picture right. And then, okay. So 7 and 3, B walks eastward. Let me come back over here. So here's the starting point. And person B is walking eastward. And they're walking kind of slow. They're walking, it says their rates are 7 to 3. So I'm just going to say 3x. Because we don't know what x is. That's the whole point. But the distance that he covers will be 3x. Now the other guy goes south and then turns, walking diagonally in such a way that they meet up at the same place. Now A's walking faster, so he has to cover more distance also. So his total distance is 7x, because they say the ratio is 3 to 7. So A is walking slightly more than twice as fast as B is. So the amount of distance that B covers is 3x. We don't even know what x is. X is like, not only is x related to time, sorry, x is like the amount of time, but it also captures like whatever speed, like it's not like 3 whatevers per hour. It's not saying that. It's saying a ratio of 3 to 7. And there's one more fact in this question. He walks 10 booths south. So we actually have a number here. This is 10, which makes this piece, because it was 7x was the whole thing, 7x minus 10. And that's our setup. 10 squared plus 3x squared equals 7x minus 10 squared. Which becomes 100 plus 9x squared equals 49x squared minus 140x plus 100. Now the hundreds cancel out. And we end up with 40x squared equals 140x, which is 40x equals 140, or x equals 14 over 4, which is 7 over 2, which is 3.5. So 3 times 3.5 is 10.5. And 7x minus 10, 7 times 3.5. What is that? 21. My head's exploding. 7 times 3 1/2 is 21 and 7/2, which is 3.5, which is 24.5. Minus 10 is 14.5. So the answer is one guy goes 10.5, the other one goes 14 plus 10, which is 24.5. Incidentally, 10, 10.5, 14.5. If you double that, you get 20, 21, 29. The 20, 21, 29 triangle comes back again? That is a really nasty question to set up. But I hope now that you've seen it, you will, you'll be able to set up a similar question. If I literally just take the same question and just change the numbers, so it won't be 3, 7, and 10, it will be 3 different numbers, but it will be the same question. So that was pretty challenging. Okay. I still want to do, because today we spent a lot of time in groups, and that's great. But tomorrow I want to start Greek math, and that takes 4 days. We only have, we only have 5 classes left, because I think on Monday before the final we'll review for the final. So we have tomorrow and then 4 other days. It's 5 days. So I have to squeeze Greek math into 3 days, and then 2 days of math from the 1600s. We actually skip ahead from BC times all the way to the 1500s for the last 2 days. So because I don't want to, I want to finish the Chinese math today, I'm going to show you one last thing. I'll do it like, I'll try to do it really efficiently for you. So you're not, so let me, there is a type of question that's called the Sea Islands. And I'm going to show you what the question is. The question is, there's this big sea island, and we don't know how tall it is. And we are over here. We're far away from it. And we put and there's like a big body of water over here. So we can't, and we don't want to get too close to the sea island anyway, because of maybe like we don't want to get too close because we're trying to attack the sea island, and we wouldn't want them to know. We want it to be a surprise. Or there's a big body of water, we're just not able to access it. So this type of question comes up. In modern day, it would look like this. We would know how many feet there are between our 2 sightings. And then we would draw these 2 lines. And we would measure these 2 angles, 2.25 degrees. And when you move closer, the angle changes, it gets bigger. It turns into 2.33 degrees.
Those are degrees, 2.3 degrees.
Degrees. I'm talking about the angle here.
Okay.
This scenario is very famous.
Sorry, how is it? 2.3?
How is what?
2.3 degree?
2.33 degrees. Now this question, if you teach algebra 2, trigonometry, this is a question that comes up in trigonometry, where the 3 known pieces of information are this distance and these 2 angles. And I'm not going to go over how you do with trigonometry because we don't need to know that way. I want to show you how in China they answered this question with no trigonometry. So I'm just going to make a note. Modern, we use trig. It's not important how we do it because some people haven't studied trig in a long time. Here's the same question. But the information is going to be given a little bit differently. Instead of talking about degrees, instead of talking about 2.25 degrees and 2.33 degrees, because if you're talking degrees, you're going to need trigonometry. You're going to need tangents, whatever. Instead, they have these poles that they set up, and they're the same size. In this case, they're both 5. And they know the distance between the 2 poles because they set up the poles. It's 1,000. Now, there's 2 more measurements they have. Here they are. They say, okay, if I put the pole here, the one that's further away, if I'm lying on the ground, how far back do I need to go so that when I look up, I see the top of the pole coinciding with the top of the sea island? So you could just kind of move back and see, and it ends up being 127 feet. Uh-oh.
Yeah, what happened?
Why did that happen? Hold on. I'll be back in a second with that. By the way, if you want to see one of the scariest pictures in all of history of math, it is the diagram for the sea island question. Huh, why is the sea island not there? Hold on a second. Yeah, it's part of the homework. This is going to turn into an algorithm. The reason, Marcus, I say it's scary is because look at the picture of the sea island.
Oh my God.
That's from like a, it's like a wood carving, ancient Chinese textbook. So there's the scary sea island. And here we are trying to measure it. So you can see why we wouldn't want to get too close to the sea island. 07.
How are they using the pole again?
I'm going to show you that in a sec. 782.450. Let me just get this thing back up.
Yeah, I'm dying to know how they got to 27.
The 127 came from, and I'll show you what this looks like. Let me just get this up and going again. So here's the way it works. Let's say, let me go to another page. You're standing, here we're looking at the sea island, right? And if you have like a stick, the stick's very small. But if you like stand, further back and you go back, the stick would look like that. If I like go back far enough, I can make it so the stick, looks like it's the same height as the sea island, because I'm like, my eye is, here's the stick. And if I could put my eye over here, when I look up, anything that's in that line of sight is going to coincide with the tip of the stick. So it's kind of weird because your person has to be buried in a hole to do this.
Kind of like when the painter uses his finger to like measure stuff.
Yes, like a painter holding up his finger and then looking. So it is a little tricky to kind of see that. But I'm telling you that if you are in the ground here, there's your eyeball, and you're looking up towards the tip of the stick, if you're 127, it's boo behind. The stick, the tip of the stick. Yeah, you could try this. Close one of your eyes. Close one of your eyes and put your finger up and kind of move your head back, and you'll see the tip of the finger will sort of go higher up, will coincide with something further and further away. Now, there's one more measurement we need. When we're 1,000 boo closer, we actually don't need to, we actually have to go back. Here's that triangle. So this is actually smaller. We only have to go back 123 feet. So the closer we are to the sea island, the less far we have to go back. It's kind of like we get like a steeper angle. We have to look up at like a steeper angle. So like, imagine I was really, really close. You'd have to be practically right next to the stick in order to do that. Whoops. So this 123 will always be smaller than the 127.
Professor, were these distances given in the problem?
Yes,
Okay, the 123 and the 127 are given to you.
there are 4 pieces of information given to you.
Okay.
The height of the sticks, which are the same, the distance between the sticks, and these 2 numbers. Now, there's going to be a formula. I'm tempted to first just tell you the formula, but since we have 5 minutes, this is actually it's not a hard problem to finish now. Here's why. Draw this line. I'll give you the formula at the end. And call this distance, call that y. And here come, although the Chinese weren't too fond of similar triangles, like the Greeks weren't, but I'm gonna modernize this a little bit. See those 2 triangles? Those are similar triangles. They're both right angles, and they're both right triangles. And this angle is equal to this angle because of that line, the hypotenuse is like the same one. If you remember your geometry, there's something called corresponding angles. Those are corresponding angles that are congruent. But even if you don't remember that, I'm telling you those 2 angles are equal. So we get similar triangles. So we can say x over y is equal to 5 over 123. Which I'm going to turn into 5y equals 123x. Now, there is another pair of similar triangles. The 5 and 127 is similar to this green triangle. And that creates the proportion x over y plus 1,000 is equal to 5 over 127, or 127x equals 5y plus 5,000. Now, what I like to do to finish this question, we were practically done. I just like to change this 5y into 123x. So 123x plus 5,000 equals 127x, which becomes 5,000 equals 4x, or x equals 1250. And that's not the sea island, because the sea island also has the extra 5. So sea island is 1255. Now I want you to notice something. If I call the pole, if I call the pole, something, what do I call it? I'll just call it B for the pole, and D for the distance between the poles, and let's call these A1 and A2. The 5,000 is B times D. And the 4 is A2 minus A1 X. So we get the formula X is equal to B times D over A2 minus A1.
Oh my God, yeah, well,
So that's a formula. If you like the formula, that will come up really easy. Oh, 126, 127. Now, I personally like the similar triangles method. So that's the similar triangles method. It's pretty nice. There's a triangle that's similar to the 5 and 123 triangle, and there's a triangle similar to the 5 and 127 triangle. Cross multiplying gets us a 5y in both equations, and that lets you do substitution and solve. This is the formula, but the island, you have to throw on a plus b there. So the answer is BD, the formula.
the D's 1,000, what's the B? What's the B?
B is the height of the stick.
Oh, okay, thank you.
D is the distance between the sticks.
Just trying to keep up with you.
And the A2 and A1 are the two these distances.
Okay, thank
Now
you.
you might say, wow, that's cool. Even if you don't know trigonometry so well anymore, you say, that's great, you could do it. But if you do know trigonometry, you're especially surprised because you're saying, how do they avoid trigonometry? Before we go, anyone know how the trigonometry is hidden in this problem? You can type it into the chat. Where is the trigonometry in this problem, do you think? How did they avoid trigonometry? Remember when I told you this angle was 2.25 degrees, like by modern ways? What does 2.25 degrees have to do with the 5 and the 127, do you think? Yeah, there's no hypotenuse, but there is an opposite and adjacent. Yeah, the answer is 5 over 127 is tangent of the angle. So when we use trigonometry nowadays, we use tangents instead of having 5 and 127. We're just told tangent of 2.25 is 5 over 127. So they avoid angles and they don't need trig because they have knowing the 5 and the 127 is the indirect way of telling me the tangent of the angle, which is what you would do with the angle anyway. If you don't know tangent, you forgot it, don't worry about it, because for homework, you're going to do the question this way. And you can see in the assignments, I have here Sea Island, and I have 2 questions. That's it. 2 Sea Island questions, you see?
That's our only
Just set
homework,
up for you.
2 things?
Yeah.
Okay.
Oh, well, I'll let everyone go, but I'm going to stick around. So you're welcome to go now. We finished Chinese math, and tomorrow, really big, we start the Greeks.
So we don't have to do part 3 of your